We're going out of order a little bit in the book, and we're going to visit section 8.7 called L'Hopital's Rule. Now, actually, the man who invented or discovered this rule or this property was French, and L'Hopital was not really his name. It was really La Hospital. It had an extra S in it, and for some reason over time, this S got omitted. For years and years, math books called it L'Hopital's Rule, and that's how I'm used to seeing it. Within the last 2 or 3 years, College Board has put the S back on his name. I'm like, you changed the guy's name? He's been dead for like hundreds of years. And yeah, evidently, I guess it should be La Hospital. So it literally translates to the hospital. All right, it's not going to hurt, though. Okay, no pain here. What you do is normally when you take limits, let's go back to chapter 1 when we were first doing limits. If I said, hey, plug a 3 in here, you'd be like, oh no, it's going to be 0 over 0, which is indeterminate. It's going to be 6 minus 6 over 9 minus 9. So what we get to do is factor. In the numerator, we'd take out the 2. In the denominator, I'd realize, oh, that's a difference of 2 squares. The x minus 3's could cancel away, leaving me with 2 over x plus 3. Remember, we now can just plug the 3 in safely, and you get 2 over 6. And of course, 2 over 6, we all know that is 1/3 when we simplify, and that would be the limit. Okay, so that wasn't too bad. But L'Hopital, or La Hospital, realized, hey, there's a easier, better way, and I don't have to factor. I couldn't teach this to you guys back in chapter 1 or in pre-calc because you didn't know what a derivative was yet. And L'Hopital used derivatives. What he did is he took the derivative of the numerator, just the numerator. The derivative of 2x minus 6 is just 2. He took the derivative of the denominator next. The derivative there is 2x. Actually, the 2's can cancel. That's just 1 over x. He plugged a 3 in, and you got 1/3. No factoring necessary. All right, that's L'Hopital's or La Hospital's rule. Now, it doesn't work all the time, of course. It only works when you have indeterminate forms. As like we've mentioned before, the indeterminate forms are 0 over 0 and infinity over infinity. If this problem comes out to be, 0 over infinity, yeah, just 0. So, don't try it when you shouldn't. Also, as I mentioned, keep in mind, this is not the quotient rule either. Even though you see fractions, you're not going to go u prime v minus uv prime over v squared. Thankfully, no. You're taking the derivative of the numerator as if it was the only thing on the page. And you take the denominator's derivative the same way. You ignore the numerator. Okay, so it's not quotient rule, thankfully. All right, let's try another. Okay, just to save you some time, I fashioned this problem to come out to be 0 over 0. If you plug the 2 in, that's what it will be. Oh, man. If you had to do this without La Hospital's rule, you would be factoring. And both of these have leading coefficients that aren't 1, so it's going to take a while to factor. In fact, I'll race you to the answer here. Go. Oh, boy. I'm going to get crushed. I even wrote the problem. I know it's got to be 2 times 1. 4 and 3, 6. 6 and 1? Yeah, that works. Okay. -5, -8, yeah, it's -13. All right, cool. The x minus 2's cancel. You plug the 2 in here and here. Let's see, 4 times 2, that's 8 minus 5, that's 3. 6 times 2, that's 12 plus 1. 3/13 is the answer from pre-calc. I know what happened. I got destroyed by you guys. Because you know calculus and you know the derivatives, you don't have to do any of this factoring. And that was not easy factoring, because most people, they look at 6 and they think of 3 times 2, not 6 times 1. Ugh. Instead, just take derivatives. So with L'Hopital's rule, and by the way, when you write it for College Board, this is a little bit annoying, but you have to say the limit as x approaches 2 for both numerator and denominator, or they deduct points. So anyway, we take the derivative here, and we get 8x minus 13. You take the derivative of the denominator, you get 12x minus 11. Now when you plug the 2 in, you get 16 minus 13, that's your 3. You plug the 2 in, you get 24 minus 11, that's your 13. No factoring, same correct answer, done. But again, you can start to see the power of derivatives behind the scenes. Besides, who likes to factor trinomials anyway? In fact, some problems you can't factor at all, like this. Remember back in pre-calc, we had to multiply by the conjugate? Ugh, I'm going to do so just to see what the answer would have been. And you remember back from chapter 1, you're like, oh, this numerator, that's just an x minus 5. That's going to cancel with this x minus 5. It'll be 1 over, and now the 5 can go in safely. The dividing by 0 issue has been removed. And that's just going to be 1 over 3 plus 3. The answer will be 1/6. Okay, hooray chapter 1, hooray pre-calc, algebra 2. We don't need to do that anymore. We know derivatives. Instead, let's bust out some L'Hopital's rule. The derivative of this, keep in mind, that's x plus 4 to the 1/2, so that'll be 1/2 x plus 4 to the go down by a power, negative a half. No chain rule, because it would be times 1. The derivative of the denominator is just a 1, which means I don't even need this fraction. This is going to turn into, let's see, 1/2, and then this will be a square root in the denominator. We plug the 5 in. That's going to be a rad 9, which is just a 3. Check it out. You got 1/6. Without having to do really anything else other than just take a couple derivatives. So L'Hopital's rule, yes. Heck, it even works with trigonometry. If I gave you this problem in chapter 1, you'd realize very quickly it's 0 over 0, but I don't think we would have been able to solve it. I mean, sure, sine of 2x is a double angle. Maybe you could pull some pre-calc into that, but I just don't think it would go anywhere. It'd be bad memories of chapter 5 from that class of trying to simplify it. Instead, just use L'Hopital's rule. The derivative of sine of 2x is cosine of 2x. Times a chain rule 2, I'll throw that in front. The denominator, of course, 1, the derivative is 0. The derivative of negative cosine of x will be positive sine of x. Now when you plug the 0 in, cosine of 0 is 1, so the numerator is 2 times 1, which would just be 2. Unfortunately, you're still dividing by 0. And since it doesn't say what side you're coming from, this is going to be a does not exist, DNE. If we were to investigate this further, I think you'd be able to see the discontinuity in the graph. I want to keep this train moving, though, so let's head on to number 5. Again, plugging in the 0 is going to give you 1 minus 1 over 3 times 0. That is 0 over 0, which is indeterminate, so we don't know where this is going. Let's use L'Hopital's rule. The derivative of cosine is negative sine, so we'll have a double negative, so it's going to be positive sine of 4x times a chain rule of 4. Denominator, 6x. Again, you want to say the limit as x approaches 0 for both of those. I know that's irritating, but that's what College Board wants you to write. So, hey, we'll play their game. Unfortunately, when you put the zeros in, you still have 0 over 0. So now what do? And the answer is, do L'Hopital's rule again. What? You're allowed to do it more than once? Oh yeah, I mean, what if this had been the original problem? And this wasn't there. I mean, shouldn't L'Hopital's rule work? Yeah. So keep doing it until you don't have 0 over 0 or infinity over infinity any longer. And it's only going to be one more step because when you take the derivative of this 6x, it will be a 6. So there's light at the end of this tunnel. Up top, the derivative of sine of 4x is cosine of 4x times the chain rule 4. There's already a 4 there, so now it's a 16. We'll make College Board happy with a pair of limit as x approaches zeros. But as you plug the 0 in here, you're going to get cosine of 0, which is 1. 16 times 1. So that's 16/6 or 8/3. Or 2 2/3. So evidently, if you graph that original black equation and you head towards 0, of course you can't be right at 0 because you'd be divided by 0, but if you get close to 0, the graph is going to get close to 2 2/3. Ooh, that's weird. I'm just curious. Let me try that out. Okay, you notice that I needed double parentheses around the numerator because I want the subtraction to happen before that division. And I also need parentheses around that 3x squared when I typed it in. Otherwise, it's going to divide by 3 and multiply by x squared. That's not what I want the calculator to do. Also, since I'm mixing trig and non-trig, like always, I want to be in radians in this class. So let me just check my mode. Okay, I'm good. And here's the graph. And as you can see, there is a hole when x is 0 right on the y-axis. And my gosh, it looks like we are heading towards 2 2/3. I mean, it looks more like 2 1/2. It's hard to tell, but we could get into the table. Let's do this. Second table set. We'll start at 0, but instead of going by 1s, let's go by 0.01s to see what it looks like. Oh my gosh, you can see it. It's heading towards 2.666 from both sides. So our answer of 8/3 is correct. L'Hospital's rule does work. That's good to know. Well, at the end of chapter 1, in section 1.5, I was plugging in infinities, top and bottom. Remember in pre-calc I taught this as well, and you probably learned it in Algebra 2 if you got that class if you had the honors level. And we said, hey, if the degree is equal between numerator and denominator, if it's a tie, you don't need the rest of this stuff, and you can just strip off the coefficients, and the answer is going to be 5/3. And it didn't seem real mathematical. It almost seemed like I was making up a story. Especially when some people are like, wait a second, you're getting rid of 3 times infinity? I'm like, yep, blowing it off. You're like, what? I'm like, the infinity squared is so much more powerful that regular infinities don't matter. That was a little shady, but actually I knew that I had L'Hopital's rule to back me up because I knew calculus, even though you guys didn't yet. I knew that plugging in the infinity would give me infinity over infinity. I knew that if I kept taking derivatives of the numerator and denominator, that eventually, not after the first time, but after the second time, the only things that would survive would be the 10 and the 6 from the largest powers, and then they could be reduced. So if you know that's going to happen, all you have to do is just stare at this. And these won't matter because when they start to have derivatives taken, they're going to fall by the wayside. Whoa. And it should make sense that if the denominator had a bigger power, let's say this was 3x to the third, then when you started taking derivatives, you'd have, 9x squared instead. Over here, this would be 18x. And 10 over 18x, remember x is still heading towards infinity. Now you've got 10 over infinity, which is why if the original is bottom heavy, the answer is 0. If the original is top heavy, it's infinity. So all that pre-calc now makes a little bit more sense because now you could see L'Hospital's rule in play. All right, let's try a multiple choice because, again, half of the AP exam is multiple choice. So if you want to pause the video to do your work before I blurt out the answer, feel free, and then you can start me back up. I'll give you a minute or so. We'll see what you can come up with here. All right, calc students, let's go. These are easy derivatives now. Aren't you glad you're not doing it the long way? Oh, man. Derivative there would be 4x minus 5. Down below, it's just simply 4. Now when you plug the 3 in, you're going to get 12 minus 5, that's 7, over 4. And you can see that 7/4 is choice C, the trick answer. Oh, oh man. Wonder how many people at home just picked that. That's not it. You guys, nobody would have missed this problem before today. There's a saying that sometimes little knowledge can be a dangerous thing. If you didn't know L'Hopital's rule, you never would have done what I just did. The problem here is this original problem wasn't a 0 over 0 case. If you plug the 3 into the denominator, it's not going to be 0. It's going to be 12 minus 7, which is 5. And if you plug a 3 into the original numerator, you're going to get 2 times 9, that's 18, minus 15. That's just 3/5, that's choice A. And the moral of the story is, even though L'Hopital's rule is cool, don't use it when you shouldn't. Remember, the problem has to be 0 over 0 or infinity over infinity, or this doesn't work. Okay, and here it was not one of those two, so be careful. All right. It's a cool shortcut, but it's not always applicable. And even though it's a cool shortcut, sometimes it just flat out fails. Like here, number 8, this is infinity over infinity when you plug it in, but you'll see that L'Hopital's rule is going to not work. I'll show you. Don't write this part down because I'm going to get rid of it soon. The derivative of the numerator is going to be 1/2 stuff to the negative half. That times the chain rule of 10. All right, cool. The derivative of the denominator, since that's x plus 1 to the half power down there. Again, it's not x plus 1 to the negative half. I mean, it is, but remember when you do L'Hopital's rule, you pretend that the fraction isn't there. All right, so it will be positive a half power in my mind. So it's 1/2 x plus 1 to the negative half, go down by a power. Chain rule there is times 1, which I won't write. The 1/2s will cancel. Since I have negative powers, they can pass through the fraction bar and go to the other side. So this will just be x plus 1 to the half, positive half up top. And this is 10x plus 1 to the positive half in the denominator. And this 10 is still up top. Oh man, look what I did. I'm back to the original. All I've done is I flipped the stupid thing upside down and now there's an extra 10. If I keep trying L'Hopital's rule, this is just going to flip over upside down forever. I'm never going to get anywhere. And so I have to find the limit some other way. So once in a while, L'Hopital's rule doesn't work. It's cool. It's just another weapon in your tool belt, but it may not be the way every time. So instead, you got to bust out some Algebra 2 or Pre-Calc. You should have learned in algebra that anytime you have a square root with a fraction, you can pull it apart or you can paste it together. I'm going to take these two square roots and paste them together and just make one square root out of it, like so. Now that we have that, we can perform L'Hopital's rule just on the inside, just on the radicand. And if we take the derivative of that part, this will just be 10. This will just be 1, because it is infinity over infinity on the inside. So the inside just becomes a 10. There's still a square root, and that is the answer, square root of 10. And if you do try this on your calculator, if you type it into y equals, and you go way out to 9999, you'll be able to see that you are approaching radical 10. It's going to be like 3.1 something, and you're like, oh my gosh, it is. Cool. All right, one more to do. The limit as x approaches pi over 2, secant of x over tangent of x. Really, I probably should say x approaches pi over 2 from the left. I think I'm going to throw that in there. We know that the graph of secant looks like a bunch of U shapes. Some are right side up, some are upside down, kind of like that. The graph of tangent is the recurring S curves. They look like this. But in both cases, secant of pi over 2 and tangent of pi over 2 are both undefined. As you head towards pi over 2 from the left, however, in both cases you will be heading on the upswing, so this is going to be an infinity over infinity situation, and so L'Hopital's rule is eligible here. But just because we're eligible to use it doesn't necessarily mean it's going to work. Let's check it out. The derivative of secant, of course, is secant x tan x. The derivative of tangent of x is secant squared of x, which of course is the same thing as secant times secant. I'm going to write it like that. Secant of x will cancel itself, and unfortunately, look, you're left with the exact same thing that we started with, except now it's upside down, and this will continue on forever if you keep trying to force L'Hopital's rule on it. It's just not going to work. So we have to evaluate the limit using some other method. And the method is the stuff we learned in Chapter 5 of Pre-Calc. Yeah. Mixed in with a little golden sheet. All right, tell you what I'm going to do. Secant of x is really the same thing as 1 over cosine of x. Now, I remember in Pre-Calc, whenever we were trying to simplify things, we always said, hey, change all the weird functions like secants and cosecants and cotangents to the three that actually have their own buttons, sines, cosines, tangents. And then take the tangents and turn them into sine over cosine. Of course, realize this isn't really a tan, it's a 1 over tan. It's a cotangent. And cotangent is not sine over cosine, it's cosine over sine, which is absolutely fine by me because the cosines cancel. And now you're just left with 1 over sine of x. Now we can put the pi over 2 directly in. In fact, we don't even need to come from the left. The sine of pi over 2, or the sine of 90, is 1. So this is going to turn into 1 over 1, which is 1. Yeah. And that concludes section 8.7. I wanted to slip it after chapter 2, in between chapter 2 and 3, because it's just cool to know this. I don't know why the book waits until chapter 8 to bust it out, because now that you know about it, you can use it in chapter 3, 4, 5, 6, 7 to your advantage. Why not? Now, there is a second half to this that only BC learns. Okay, so I've told you the truth, but not the whole truth. If you want to learn about that, take the class next year, and you'll get to learn behind the scenes. This goes on. It's about twice as long as what I'm going to show you. But everything that you need to know for AB has now been taught. So until we meet again, take care.